So in the first fit algorithm, as we have seen in the fixed size, okay, even though for the variable size, first fit algorithm was performed better, okay, in case of fixed size, first fit algorithm actually shown us the problem of external fragmentation, okay, and also internal fragmentation as well. So externally, how much memory we have left? If you calculate that, is internally you have lost 350, 390 for this process, 43 for this process, and 32. So this is our internal fragmentation, that is 465, and this is our external fragmentation of 491. So we have this, but we cannot allocate the memory. Same we go for the next one. In the best fit, let's go for the worst fit. Best fit. So in the best fit algorithm, what we do, we search for the smallest space or a smallest empty block fit enough to allocate the memory. So which one here is the smallest to fit? Wait just a minute. 357. Someone joined. Okay. So which one here is fit as smallest for 357? So this one 400, 600, 500. Out we can store process one, that is 357, in any of these three. But the best fit algorithm chooses the smallest one. So it will store here 400. Okay. Okay, nice. Let's go for the next case. So process one will be stored into 400. For the process two, we have this option 600, 500, 300, and 250. Which one is the smallest one? 250, right? So it will be stored here in this one. For the process three, we have this option and this option. Which one is the smallest? This one, 500. So it will be stored here. Then process four will be stored here. So not only we could store all the memories, all the processes, but also the fragmentation, internal fragmentation was very, very low. Okay, only 224. Now, and is there any external fragmentation? No, we have allocated memory for all the processes, so no external fragmentation. And finally, in the worst fit algorithm, what we do, we always search for the highest space. So if I want to store 357, I will, which one is the highest here? The largest, 600, right? So I will use 600. And if you see that it will be stored here, and already there is a internal fragmentation of 243. That means this space are wasted. Then for 210, which one is the largest? 500. I will store 210 here. So 190 fragmentation. Then if I want to store 468, no space left. So I cannot allocate P3 and P4. So all these two processes are external fragmentation. That means process that could not be allocated memory. So what is our conclusion from learning this? Okay, that we have two types of memory allocation, that is variable size and the fixed size. Okay, for both cases, okay, in the contiguous memory allocation, we have fixed size partitioning and variable size partitioning. In both cases, we have three algorithms: first fit, best fit, and worst fit. What the first fit does, it allocates memory that is that it finds first. In the best fit, it searches all the memory and it allocates to the lowest one, smallest one, that is fit enough to store the process. And the worst fit, it actually finds the highest, largest memory, and then it allocates it to the process. So in the fixed size partitioning, okay, the best fit algorithm is the best, okay, but in variable size partitioning, first fit and worst fit are the better options. Okay, and also what we have seen, that there are two types of fragmentation. One is internal fragmentation, that is the memory that is gets wasted because of allocating in the process. Okay, and another external fragmentation, that is the process that we could not allocate. So in this one, okay, in the fixed size, which process we could not allocate? P4. So the external fragmentation is 491. Why? Because the size of the P4 is 491. In the best fit algorithm, okay, there is no external fragmentation. Why? Because we have allocated memory for all the spaces. And in the worst fit algorithm, what is the external fragmentation? 959. Why? Because we couldn't allocate process 3 and 4. So this is how the physical memory gets divided into between different processes. Okay. Now here's an exercise, you can practice it on your own. Okay, and you can find out the different the for best fit and the first fit and the worst fits, how the partitioning will work. Now there's one last thing about from this topic is that yes, we understand, remember this topic that we learned, swapping, that the process can be swapped in and swapped out from the memory. Okay, so whenever we are swapping in, okay, a process temporarily from main memory to the storage, okay, there is so let's assume this is my CPU main memory, and for any reason there we have learned different reasons for swapping. I am swapping this out and swapping process to in. Okay, so sometimes what we have to do, okay, we have to actually take care of logical and physical address space. So we'll not focus here right now. Okay, our main focus is this one. Okay, let's assume that I have two type of address. This is my main memory and this is my CPU. Okay, now what I will do, I will convert a logical address to a physical address. So first of all, we have to know, right, what is a physical address and what is a logical address. Just think like this. You have declared an array of size 5. So the array have 5 location, array 0, array 1, array 2, array 3, array 4, array 5. Okay, now my question is to you, whenever you are trying to print array 0 in your code, okay, the value that you store, okay, there is actually nothing called array 0. This is just a variable. Okay, what it will do, it will actually go to the memory location and it will print the address of that physical address of that variable. Okay, sorry, the data is stored into that physical address. So by mistake, what many of you did, I think, that whenever you are actually learning your C programming, okay, instead of writing printf %d then the array I, many of you by mistake have printed and array I, and it actually used to print a garbage value. Basically, it was not a garbage value, it was actually the address, the physical address of the main memory. So what I'm trying to say here, that whenever you declare an array of size 5, A0, A1, A2, A3, these are logical addresses, okay, for the CPU, that I want to store data into A0, I want to store data into A1, I want to store data into A2, A3, A4. Okay, but actually the data actually gets stored into some physical memory where the address actually are much more complicated, like they have a huge address. Okay, so what this does, this actually converts a logical address to a physical address. Okay, and to that, for doing that, it needs two register. One is called limit register and is called relocation register. So what it does, okay, it first takes the logical address, let's assume array 0. Okay, and it first checks that the data that you want to store, is it actually valid or not? But that means whether you are within your limit or not. So if I think about the example that I'm talking, let's assume I have an array of size 5. Okay, so if I want to if I want to access array 10, okay, this is actually not I don't have any permission for that. Okay, this is actually not permissible. It is beyond my limit because the limit of my array is 5. Okay, so there is nothing called array 10. So this will actually, the limit register will check that whether you are within your limit or not. Your limit is from 0 to 5. Okay, and if you're not within your limit, if you're not, it will go to a trap. That means it will generate an error. Okay, but if you're within your limit, if you want to access from array 0 to array 5, it will say, okay, yes, go ahead. And then using a relocation register, it will actually do some math, plus minus operation, and it will actually make sure that you can access the actual main memory. Now, we understand that what happens here, we convert a logical address. First, we check whether we have the permission or not, and then we actually use the relocation register to find the memory. Now, how does this work? I will show you another example. It will be very 100% clear. So the relocation register, what it does, it actually holds a value. Okay, the value is that it will target you, or it will actually drive you, or it will actually, how should I put it, it will actually direct you to the actual address. So like if we are talking about this examples here, so LR, okay, RR,
Okay.
LA, okay, all this, what does this mean? So this is process 0. Okay, and for the process 0, we have to calculate the physical address. That means where the process is actually situated. Okay, so we have declared an array 0 to array 5. Okay, and what we want to do in this exercise, we want to actually calculate that where this arrays are actually stored into my computer's memory. What is the actual physical address? Okay, now, so we know what PM is, physical address. Okay, then LM is logical address. So what does RR means? So we have to go back here. Relocation registers and limit registers, LR, RR. So LR means relocation register, RR means limit register and relocation register. So what does this two do? This limit register, it says 500, and what does this mean? This means that this LR, okay, that means the limit register, the process P0 have access from array 0 to array 500. Okay, this is actually, to put it in a very simple term, this is not the actual meaning, but this 500, the limit registers means that you can access from array 0 to array 500. Relocation register means that if you add, okay, 1200 with this address, you will get the physical address, and logical address is the location. So let's see one example. So okay, where is the answers? Okay, it's not given here, I have to calculate myself. So basically what you have to do, okay, let me show you this example. It's already done here. So the logical address was 346. That means go to the array address of 346. So array 346. Okay, so what it will do, it will go to the relocation register, which will say that the array 0 is situated into the memory address of 14,000. So what it will do, it will add these two numbers, and it will actually go to the physical address 14,346, and it will find your value. So now if you think of it, it's very simple. CPU stores an array from 0 to 500. Okay, so it will say I want to access array 0, so it will be 40,000 plus 0. If I say I want to access array 1, it will be 40,000 plus 1. If I say I want to access array 346, it will be 14,000 plus 346. Now it's very simple, right? Just I'm doing some add operation and I'm accessing the physical memory. So relocation register, what it does, it actually keep tracks of all this memory. Like for this array A, it is 14,000. For array B, or I can say for this might be 200. Okay, for array C, it might be 300. So this example, the one that I have shown you just a little bit ago, okay, this actually holds the address for different process. So for process 0, the relocation register value is 1200. For process 1, the relocation register is 550. For process 2, it's 880. So that means if you want to access this 300 location, array 450, okay, you just have to add this 2. If you want to access array 300, you just have to add this 2. If you want to access array 210, you just have to add this 2. If you want to access P3, you just have to add this 2. If you want to access 80, you just have to add this 2. So this is the array index that will be given to, or that you want to access. Okay, this is the physical address that you have to calculate. And what does this mean? Okay, so I have said, so this basically actually what it does, it actually limits that you cannot go beyond that. So if you look closely, you see this is 300 and this is 275. So what I'm trying to do, I'm trying to access logical address 300, or I can say I'm trying to access array 300. But the limit registers have already said that for this program, you're only allowed to go up to 275. So that means this is actually trap. Okay, so this physical address will not be calculated. So this one will be a trap. So again, let's go here. Is there any other trap? No. So this was the only trap. So this one is very close, but this is within the limit. This is also very, okay, this is another trap. Okay, you are trying to access array 450, but your limit is only 420. So this is another trap. And same, so yes, no other traps are here. So we can finish here. So this is all about our physical memory allocations and address translations.